Hello everyone, welcome back. In this unit, you will learn the basics of how we employed Vensim software for system dynamics modeling in the Emphasis project. In the Emphasis project, we developed 3 system dynamic models using Vensim. This is a software specifically designed for system dynamics and simulations. In this session, I will walk you through the main features of this model. 3 behavioral models were created, each representing a different transition pathway for the future of the EU agricultural system. These models are behavioral and allow us to run simulations. We can observe how variables interact and how they and the system evolve over time, influencing each other. This is what makes the model dynamic. We can also create scenarios by changing assumptions and running simulations. The results of any model simulations are endogenous. It means that we are not introducing external shocks to change the results, but rather changing some initial values in order to elicit different final results. Simulations are run on a yearly basis, over 10 years. This time frame helps us capture meaningful dynamics, without going too far into the future, because the further we go and the less notable and relevant are the results. The goal here is not prediction, it is understanding potential trajectories of behavior, understanding how change happens. So, what do the models actually allow us to do? They allow us to answer this question: what could the future of selected variables of the EU farming system look like over 3 strategic implementation pathways over the course of the next 10 years? For the purpose of this session, we give you as examples the main variables of the low-input agriculture model. These variables do not represent the accumulation of resources, but rather different system configurations reciprocally shaped by behavioral dynamics. Some of the variables included in the low-input agriculture model are policy and governance support, so how much do public actors intervene in making the adoption of sustainable practices doable, or economic viability for farmers, so to what extent do farms stay economically viable and accumulate capital, or farmers' motivation, so how much are farmers intrinsically motivated to undertake sustainable practices, or knowledge and expertise access, so how much knowledge do farmers have in regards to sustainable practices. And finally, sustainable agriculture adoption rate. This last one is our main outcome variable. It is what we measure the performance of each scenario on. How much did those circumstances we were testing increase the level of adoption of sustainable practices? The model includes stocks, flows, and auxiliary variables. All variables are connected through causal relationships. As previously defined, stocks represent accumulation, but are united by behavioral dynamics. Stocks change over time. They increase through inflows and decrease through outflows. Flows define the speed of change, and everything is interconnected. Take economic viability for farmers, for example. It is a stock, it has an inflow and an outflow. Its value changes over time based on interactions with other variables, expressed through connections of this inflow and outflow with other variables. Let's have a look on how a stock presents itself more specifically in the Emphasis system dynamic model. We express stocks with unit fraction and equation type level to correctly portray them. Each stock has an initial value. All values are normalized between 0 and 1. This ensures model stability. The new values each variable can take over time depend on their causes. These relationships are visible in the model structure. Zooming out, we can observe relationships are not portrayed directly. We use auxiliary variables, such as policy and governance support influence on economic viability for farmers, to portray the influence of a stock on another. Therefore, causal relationships are portrayed unilaterally. These represent influences. And we also use constants. They define the strength of these relationships. Auxiliary variables, on the other hand, define the speed and shape of relationships between variables. Zooming for a moment in on flows, in this case increase of economic viability for farmers, so the inflow of economic viability for farmers, we can notice they are expressed as fractions per year with equation type auxiliary. They do not accumulate. They only define change and dictate the speed of increase or decrease of stocks. Zooming back on auxiliary variables, on the other hand, we can notice they are expressed similarly to flows, therefore with the same unit and type of equation, but carry a different meaning. They are not directly impacting the accumulation or decumulation of a stock, but rather mediate their relationship. They help connect variables. To portray these influences, we employ functions that show the delay of causal relationship between these variables. In this case, we employ smooth tree. This introduces delays. For example, a policy does not have immediate effects, but can activate after a certain time frame, namely 3 years in this example. We also use lookup functions. These allow non-linear relationships. For example, a slow start, then acceleration, and then saturation. Our relationships are first defined qualitatively through the literature and then translated into equations. Constants, on the other hand, represent the strength of our relationship, while the functions shown before represent shapes and speeds. Constants are dimensionless. Their values are based on literature, much like the other dynamics. They do not define shape or relations, only intensity. Here we see a simulation of the variable of economic viability for farmers. The same output can be simulated for any stock variable in the model. We can see here that economic viability decreases over time, but gradually. This makes us think that the result is realistic. We can test model robustness with sensitivity analysis. Finally, let's have a look at the adoption rate. This is the key result for the scope of emphasis project. In this case, we see a steady increase. This suggests a positive system dynamic in terms of sustainable transition. To conclude, this model helps us understand complexity. It allows us to test scenarios and explore how change happens. Not predict, but understand. Thank you.